And I do want to go over a couple things from last time, and then I will. And actually, this is a good day if people had to miss it. This would be a good day because I'll be covering chapter 4 today, and I realized in the original schedule I allowed two sessions for chapter 4, but I don't think that's necessary. I think I can cover what I need to cover tonight. All right, even after I review what we did last time. All right. So what I'm going to do is I want to share a screen with you guys. And we ended last time with near the end of the last session, we were looking at this problem 3.32 on page 83. Okay. And what I did was I wanted to show you, write out for you what the solution looks like for these 4 parts of the problem. And so I believe it had to do with light bulbs or something, if I'm not mistaken. And just look at it one more time. Yeah, these are extended life light bulbs with an average life of 12,000 hours and a standard deviation of 500 hours. So notice on the top here, I write this in the with the Greek letters. Mu means the population mean. Sigma, small sigma here, means population standard deviation. And here is your formula for converting what I would call a raw score or raw value, means the original value in the original units, to a standardized z-score. So you take your original value, whatever x is, that's your original number. You subtract the mean, that's your numerator, and you divide that difference by the standard deviation, and you get a unitless result, which is a z-score, a standard score. And what the z-score tells you is for any particular value of x, how many standard deviations to the left or to the right is this value from the mean, okay? How many standard deviations from the mean is this value? If it's a negative number, if the z-score is negative, it means it's to the left, and if it's positive, it's to the right. If it's 0, it means that the value is exactly equal to the mean, right? Because if x is equal to mu, then the numerator becomes 0. All right, so this first question said to approximate the percentage of data, or I guess the percentage of light bulbs in general, that would be between 11,000 hours and 13,000 hours. So what you do is the easiest way of doing this is to convert each of these what we call raw scores or raw values, the original values, into z-scores, standard values. So the 11,000, notice I said z 11,000 just so you can see the notation. It's 11,000 minus 12,000 divided by 500, which if you do the arithmetic, it's -2. So relative to the mean of 12,000, 11,000 is 2 standard deviations to the left of the mean. Okay, that's what -2 means. For 13,000, we do the same arithmetic, plug it into the z formula, and we get +2. So this indicates that 13,000 is 2 standard deviations to the right of the mean. And you can draw a bell-shaped curve like this. And this bell-shaped curve is for the z-scores, for the standard scores. Picture this. You've converted all of the original numbers to z's. And now you have this z-curve. And if you remember, when we did this in Minitab last time, we know that the z-curve will have a mean of 0 and a standard deviation of 1. Okay? So the mean is 0. And 2 is somewhere out here to the right of 0, and -2 is somewhere out here to the left of 0. And because this curve is symmetric, the distance, the area under here, the area under the curve between 0 and 2 is the same area from -2 to 0. It's called symmetry. All right, this is a symmetric curve. All right, so you'll learn more about this a little bit later, but the area under the curve tells you the percentage of values that are in between two values. So from 0 to 2, this area here is the percentage. And it's the percentage of light bulbs, a percentage of light bulbs that have hours between 0 and has the standard scores between 0 and 2, or another way of saying it, that have hours of lifetime hours between 12,000 and 13,000. Okay. And then this area here from -2 to 0 is the percentage that's between 11,000 and 12,000 hours. And the area tells you the percentage. All right. You get the idea? The area under the curve gives you the percentage. So we know that from the empirical rule, which we learned, that plus or minus 2 standard deviations from the mean, the percentage is 95%. And again, the z-scores give you the number of standard deviations from the mean. So in this case, it's from -2 to 2. So this whole area under here is 95%. All right? So that's the answer. Approximately 95% of all the light bulbs, of these types of light bulbs, will have number of hours that they will last will be between 11,000 and 13,000 hours. All right? Any questions about that one? Then it asked about approximately, yes, Mo, you have a question?
No. No, I just said no, thanks, sorry.
All right. And then the next one asked about the approximate percentage over 12,500 hours. Well, 12,500 hours, if you convert 12,500 to a z-score, you get 1. So 12,500 is 1 standard deviation to the right of the mean. We know that between that plus or minus 1 standard deviation from the mean of a bell-shaped curve, according to the empirical rule, is 68%. 68%. So if I had a -1 over here, the area in between -1 and 1 would be 68%. But because of symmetry, there's 32% left. Half of it's going to be to the right, and half of it's going to be to the left. And half of 32 is 16%. That's where we got that. That's where I got 16%. So I said here between z is equal to 1 and z is equal to -1 is 68%. That's the empirical rule. Therefore, that leaves 32%. 100 minus 68 is 32%. Half of that 32% goes to the left tail. So if you can picture a -1 here, the left tail, to the left of that -1 would be 16%. And then the other half, 16%, is on this right tail. The answer to this question is 16%. Everybody okay with that? Steve, you look a little not sure.
Yes.
You're okay. Okay. I wasn't sure whether the yes meant you're unsure, whether you're okay.
Yeah, sorry, I think my audio played.
Okay. All right. Part C said, how about the percentage is less than 11,000? Well, we know that 11,000 is -2 standard deviations from the mean. It's 2 standard deviations to the left of the mean. We know between -2 and 2 is 95%. What's left is 5%, right? And that means half of the 5%, or 2.5%, will be on the left tail. The other 2.5% will be in the right tail. So the answer to this question is 2.5%. And finally, the last one's probably the most difficult one of the 4 here. We wanted to know the percentage of lifetimes between 11,500 hours and 13,000 hours. Well, we haven't figured out the z-score of 11,500. Well, it's -1 when we use the z-score formula. So if you look at this curve here, what we're asking for, what I'm asking for, the book's asking for, is what area is under the curve here between -1 and 2, because 13,000, remember, was z is equal to 2. We did that earlier. Well, we know between -1 and 1 is 68%, so to the left of -1 must be 16%. Between -2 and 2 is 95%. To the right of 2 is 2.5%. This is just, to me, it's the simplest way of doing this. So the left tail is 16%. The right tail is 2.5%. If you add the tails, now these aren't symmetric, right? And they wouldn't be. If you add the tails together, you get 18.5%. What's left is what's in between. So if you take 100% and subtract 18.5%, you get 81.5%. That's how you came up with that answer. Are both of you okay? Mo, you're okay with that?
Got it?
Okay, Steve, you're good. All right, so I will be posting this on in Canvas for you. A couple things, PDFs I'm posting. This is one of them. So this will be a reminder of how to use the empirical rule. All right. Okay, so that is that. And I also wanted to explain to you in that special project I wanted you to do. And this has to do with problem, and what I'm going to do an example like this. I'll show you. This is problem 3.41 on page 86. So we'll get to the next page here. 3.41, page 86. Now, what you're given in this problem is a frequency distribution table. Okay. This is what we created, you know, previously when we, that was one of the first things we did, right? We created a frequency distribution table, and then we created a histogram based off of it. So suppose you had, if you look on 3.41, it says that there are 80 packages that have been randomly selected from a frozen food warehouse. The age in weeks of each package is identified. Given the frequency distribution shown, and what the frequency distribution table, if you don't have the book in front of you, shows, it has a column for age in weeks and a column in number of packages. So the age in weeks is in categories. There are 6 categories. So the age of these packages in weeks go, the first category or class goes from 0 to up to, but not including 10 weeks. The second is from 10 up to, but not including 20. Third one goes from 20 up to 30, not including 30. 30 to up to 40, 40 to 50, and 50 to 60. And then there is a list after that of the number of packages. Well, that's the frequency, right? And they're counting the number of packages. That's the frequency. This is a frequency distribution table. If you added up all the frequencies, it would come up to 80. So what I'm going to do is I'll go to Minitab. I did this in Minitab. Oops. Sorry about that. Minitab. And what you can see here is I created the lower and the upper boundaries for the each class. And I put them in separate columns so I could just ask Minitab to calculate the midpoint. Remember, the midpoint of any class is the middle value, and you just take the average of the lower and upper endpoints. Okay? And so we got these numbers here. And if you just go to Calc, I mean, I'm sure you can do this without me showing you, but if I did C3 here and did a tab, that's my formula, right? Lower plus upper divided by 2. Okay. Now, we're assuming here that we do not have the original data. All right? There's no original data here. And this is the only thing that you were given as a person to approximate the mean and standard deviation of the ages of the package. Now, if you had the original data, why bother doing it this way, right? It doesn't make any sense. But suppose the original data was thrown away and you had to work strictly with the frequency distribution table. And you wanted to come up with an approximation for the mean and standard deviation. Now, what we're essentially doing here in this problem, we're essentially replacing the individual values with these midpoints. Now, here are the frequencies. So we don't know, we know that there are 25 of these packages that have been around from 0 up to 10 weeks. All right, and they had different number of weeks that they were there. But since we don't have that data, we're going to assume, we're making this broad assumption here, that every single one of these 25 packages it's been around for 5 weeks. Okay? That's what the midpoint is displaying here for you. All right? It's telling you it's the representative value for that class number 1. We don't know the actual values for class 1. Same thing with class 2, class 3, all the way down to the last class. Okay? Now you notice that the width of each of these intervals is 10, right? And notice the midpoints are 10 apart. That's the way it should work. Here are your frequencies. So, if you remember to find the mean in general, what is the mean? If we had the original individual values, we simply add them all up and divide by the number of them, right? And that would be our mean. Well, we're doing essentially the same thing with this formula, m times f. M is representing the midpoint. When I say 5 times 25, right? 5 times 25, that should be the sum of those 25, sum of the weeks for those 25 packages. Okay? And I do that for each one of these rows here, and then I add them up. That should be the grand total number of weeks. Now, it's an approximation, right? Because we don't know the actual number of weeks for each package. But if we simply multiply 5 times 25 and then 15 times 17, go all the way down and do that, and then add them all up and divide by how many packages? 80, right? The sum of all the frequencies. We should get the approximated mean. So it's the sum of this column divided by the sum of this column. Gives you the approximated mean. See, so, you know, if we look at C5, which is the column where we multiply the midpoint times the frequency, C5 here, and you can see that's what I'm doing, right? Midpoint times frequency. And then if you do C6, and let's change that to C6. Notice I took the sum of the column of the m times f. That should give me my total sum. And I'm dividing by the total frequencies, which is the total number of data points in the data set. And that's how I got 21.75. Okay? Does that make sense?
Yes.
Then, all right. Now, in the book, let's just go back to the PDF that I created. Where are you? Here it is. All right, so let's go to the, it's this page. It's the second page of this PDF. So, step 1, to do this type of problem, find the midpoints. Step 2, approximate the mean using this formula. This is the formula that I used, right? The sum of the products of the frequencies times the midpoints divided by the sum of the frequencies gives you the approximated mean. I use this little wiggly line instead of X bar as my symbol for the approximated mean. book didn't do it, I did it. So, for this approximated variance, this is a shortcut formula for it. Look at the numerator. It's saying to do the following. It's saying, I want to add up the product of the frequency times the midpoint squared. The frequency times the midpoint squared for each value. And then I want to subtract from that the number of values in the data set times the approximated mean squared. So that's that whole thing there is my numerator. And my denominator is the number of data points minus 1. And that gives me the sample variance. Okay? The numerator here, by the way, this is sort of a easier way to calculate the sum of the, I mean, if you wanted to do this, you'd have to, the original formula, you would have to take the deviations from each, the midpoint deviations from each of the means, the approximated means, right? Square it and then multiply it by the frequency. Okay, for that. It looks complicated, but this is the what the book came up with is an equivalent formula for this, for the numerator. It's equivalent. All right. So you take, again, f, the frequency, times the midpoint squared. You take the sum of all those. Right? And then you subtract 80 times the mean, the approximated mean squared. Now you can do this for each line of the spreadsheet. All right. So that's what I did. I created this formula for each line of the spreadsheet. Well, actually, I didn't do that. No, you can just simply do this, do it the way it's shown here. So take the sum of these, subtract 80, in this case, times the mean squared, and divide by 80 minus 1. So let's go back to the spreadsheet. Notice what I did was in C7, since I need m squared, to be f times m squared, I needed to find m squared first, so I simply created a column that just squared the C3s. The C7 is just C3 squared. Okay, so C7. So the midpoint squared. This is the C3 squared. And I get this column. This column here is F, which is C4 times C7. The C4 times C7 is F times M squared. And I get this column. To get the approximated variance, it's C9. Let's go to C9 here. This is where it looks kind of complicated. This is C9. So what is C9 is saying here? Well, the numerator, everything to the left of this slash, this slanted line here, all this is the numerator. I have the sum of what? Fm squared. Right? That's the sum of this column here. Sum of C8. That's what this is. Sum of C8. And then I subtract what? 80, right? Now 80 is what? The sum of C4, the sum of the frequencies. Times C6 squared. What's C6? C6 is the mean squared.
I hate to slow your roll, but I can't see the mini tab on the screen. Are you screen sharing currently?
Oh, I'm sorry. I didn't. Thank you for letting me know that. I didn't screen share it. I thought I did, but I didn't. All right. Let me go back.
Thank you.
Yeah. Thank you for, yeah, I always want you to do that is, so I did quite a bit of that without you seeing it. All right. Let's actually cancel out. Let me do this again. M squared is the midpoint squared. So I just did C3 squared. F times M squared. F is C4 times C7. That's where I got this column. Now the variance formula, that's C, I put it in C9. You did see the formula I showed you before, right? Yes?
The one on the piece of on the PDF.
Yes.
Yeah.
All right. That's what this is here. Everything to the left of this slanted line is the numerator. Okay? What's the numerator say? I want to take the sum of FM squared. That's what this is here, right? The sum of FM squared. It's the sum of C8 minus the product of what? Minus the product of what? It's the 80, right? The 80 is the sum of C4, the frequencies, times. What's C6? It's the mean squared. This number here, C6 squared. So the sum of F times M squared minus 80 times the mean squared is the numerator. That's that formula I showed you earlier. The denominator is 80 minus 1. 80 is the sum of what? C4.
All the frequencies.
Right, minus 1. Just make sure you put them in parentheses. So, and then if you click OK, you get 245 even. And of course, standard deviation is simply the square root of 245. And if you round it to 2 decimal places, it's 15.65. Now you can do this in a spreadsheet also, but you could do it in Minitab. I just showed you how to do it in Minitab. It works. This is how you come up with an approximated mean, an approximated standard deviation when you have a grouped data in the form of a frequency distribution table. This table here, right? It's this plus the frequencies is your distribution table, right? Given that, so step 1 is create your midpoints to represent the values in each class. Step 2 is to calculate the mean by taking the product of each of these and adding them up and dividing by 80, the sum of these, sum of the frequencies. And then to get the variance, you need to square the midpoints, multiply those squared midpoints by the frequency, right? And then the approximated variance says add these up here, add up this column here, right? Subtract from that the sum of this, which is 80, times what? Times this number squared. That's your numerator. And you divide by what? The sum of this, which is 80, minus 1. And you get 245. And then this is just the square root of 245. So what I'm going to ask you to do as a SPA project is I'm going to give you another one of these in the book, right? It'll be problem 3.40. And we'll send out a little email to that effect. And I want you to do this, what I just showed you, right? You won't have the solution in the book. This is in your, this solution's in the back of your book. But that's going to be your project, is you can do it either in Excel or Minitab. You might as well do it in Minitab since you're becoming familiar with it, right? So you might as well do it in Minitab. And just set it up just like this. And that'll be a project that you'll work on. And I will have you work on it, and it'll be due next Tuesday, all right? So you have a few days over the weekend. It shouldn't take you long. I'd say no more than half an hour, right? I will post this. I will post, and then once I post it, you'll be able to load it into your Minitab, and you'll be able to look at all the formulas and everything and review it again for yourself, all right? All right. So that's what you'll be working on, one of the things you'll be working on next few days. All right. Any questions about that? No questions? Okay. All right, so let's stop sharing. And let's go back to yeah, I didn't get a chance. My scanner was acting up, so I didn't get a chance to scan chapter 4. But I'm going to open up PowerPoint for chapter 4, and I'm going to point out to you in the I'm going to post this PowerPoint, of course. What you need to know, because there's some terminology in here that you don't really see very much in other textbooks, but it's okay. So we're not going to spend more than today on this, because the only thing I can tell you about this particular chapter is it's going to tell you a little bit about probability sampling, the idea of probability sampling. There are some, if you read through the chapter, you will see that they go through the different types of studies, research studies that you can come up with. And this is an elementary book, so you have to realize what they're talking about is extremely elementary. Elementary meaning very beginning. There's so many different types of studies in today's world. I mean, this list, it would go endless. There'd be hundreds of different types of studies that people have come up with, all right? Different types of techniques, and you can get extremely complicated with this. So that's why I'm a little surprised they went into even this much detail. Usually an introductory book, they break up the types of studies into 2 groups, which are called observational versus experimental studies, all right? But they talk about exploratory, which means that you're initially, you know, you don't know much about your subject, so you're exploring, right? You want to see which variables are important for the type of thing that you want to do, so you do an exploratory study. There's descriptive studies where you're just looking and describing what you're seeing. There's studies that you may want to, maybe you have a theory about cause and effect, causal study, or maybe you want to make a prediction, some sort of prediction. Fine. I don't see the point of going through all of this because you're not going to be doing very much of any of this in this course, to be honest with you. This is supposed to, you know, a lot of what they're saying here would be for a graduate level course, maybe, you know. So I wouldn't worry about these descriptions so much. Just know what, you know, in general what they mean, very generally. They also go into, and this, again, this is something that would be more important if you were actually going to do some research. The difference between primary data sources and secondary data sources. A primary data source would be that which you have created yourself as a researcher. So let's say you created a questionnaire and you're doing your own survey, right? Not somebody else's survey that they created. You're doing your own survey. So that's a primary data source. A secondary data source is using data from somebody else. And you're doing research on that. Maybe somebody else used the data for something for one topic, and you're going to use it for another topic. And what's internal versus external mean? Internal means internal to your organization. External means external to your organization. All right. If it's just you, then it's I don't know what it means by being internal to you. Is it inside your body? I don't know. But this only pertains to if you were working for a company. That's what I'm saying. They're just throwing so much stuff at you in this chapter. You can easily get overwhelmed with the terminology. So I'm going to make it easy for you and say, just read through this and don't worry about difference between primary and secondary, because you're not going to be, it doesn't matter in this course at all. Everything's going to be secondary. I'm not going to be asking you to do your own research in this course, all right? No time for it, and I would spend so much time teaching you how to do it that you wouldn't even have time for anything else. Now, what is important, and I will post this. I wanted to post it, but my scanner was acting up. But I'll ask my scanner to cooperate. Is sampling design? Sampling. Now, sampling is the procedure in which you acquire participants for your study. So you're doing a primary study, okay? And you are going to be acquiring people, participants for your study. Now, you could be acquiring them for an observational study or an experiment. I'll tell you the difference between those two in a minute. But a sampling design would mean, are we going to be using a probability sample versus a non-probability sample? Now, this is critical because everything we're going to do from this course, for this point forward, assumes a probability sample. Otherwise, why bother with studying probability? It wouldn't help. Why bother learning about what's called inference, which is taking data, the data from your sample and generalizing it to your population? We can't do any of that without probability in a modern sense. Without probability, whatever you've done only pertains to what you're looking at. That's it. So all of these polls that are done, political polls that are just, these pop-up polls or the ones over the internet, if they're not based off of probability, they're a waste of time and effort, and they're just there to influence you. They are I'm telling you, complete waste of time. Might as well have not done any of it, unless there's some sort of reason why the people who produce the poll want you to see it, because they're trying to influence you in some way. Now, the probability sampling design is not very old. It's Gallup. George Gallup was the very first person to ever use it in the political world. And when did he first use it? In 1936. The 36 election between Franklin Delano Roosevelt, who was running for president again, and I believe his Republican opponent was Alf Landon, who I believe, if I'm not mistaken, was the governor of New York. Anyway, there was a very big magazine back then that the subscribers of which were basically Republicans, wealthy Republicans. Right? Most of the subscribers to this magazine. People who were poor didn't read this magazine. People who were well off read this magazine. And the people who read this magazine hated Franklin Delano Roosevelt. They hated him because he was distributing money to the poor people, and they didn't want that. They wanted the money all to themselves. Sounds familiar, right? And anyway, they did a poll through this magazine. In other words, the subscribers to this magazine were polled. They ended up, now I believe there was like 10 million people subscribed to the magazine, 2 million of which responded. And the poll showed that Alf Landon would beat Franklin Delano Roosevelt 2-1. Wasn't even close. But the subscribers were biased, weren't they? They were biased. Did they represent the population as a whole? Well, apparently they didn't, because it turned out the election went the other way around. FDR won 2-1. Now, George Gallup, this young guy who nobody cared to listen to, because he was in his 20s or 30s, whatever. He used probability-based sampling. He learned about it. He decided to apply it in the political arena. So he became like a trailblazer. And he was the sole person who predicted FDR would win by a landslide. And he was right. In this magazine that had been around for years and years, that apparently predicted all of the other elections, because many of those elections were won by Republicans, they were embarrassed. And they actually went out of business. People stopped subscribing to them because they had it so wrong. And George Gallup, of course, you've heard, of course, Gallup. The name Gallup is famous now. But nobody knew about him at all. He really was a single person going against this giant machine. And David against Goliath, and he won. And The reason it won because he used probability sampling. And his sample was much smaller than the magazine sample. The magazine ended up with 2 million people in the sample. He had in his sample like several thousand. That was it, like a couple thousand people. And everybody's laughing at him. How can you possibly predict what millions of people are going to do in the poll with a couple thousand people? And yet he did. So he's the one who came up with this idea. So it's not very old, right? 80 years old, 85 years old, something like that. So we need to differentiate between probability-based sampling and non-probability-based sampling. And we also have to differentiate the type of errors that come up through this type of sampling. We call them sampling errors versus non-sampling errors. Okay. So these are sort of the terms that they're using in the chapter. And what it's mentioned to you is that you need to pay attention to this section right here, the probability samples. And then they mention these non-probability samples, which you should be familiar with. But the ones above here are the most important ones. And again, the types of studies, they mention them here. They talk about the research process, which again, kind of fun to look at, but again, you're not going to be doing this in this course because you're not creating your own research. But it does make sense that you would define your problem first, right? Steve, you got a PhD. You probably did a dissertation, right? And
Yes.
you had, yes. And yeah, you're probably like, oh, I'm glad that's over with. I don't have to think about that again. So I'm bringing back a bad memory. My wife also had a dissertation to do, and nobody likes it. Nobody likes doing this. But if you remember, and it probably
It is horrible.
it's horrible. And one of the first things that one of the most horrible things that you had to do was find a topic that your research committee accepted. And it had, you came up with this probably came up with this really good idea, right? You thought, I'm going to run with this. And it got rejected probably, right? And then you came up with something else and got rejected again. And it was just multiple iterations of this. And finally, they said it has to be so minute, right? Because it has to be so specific. So defining the problem means defining it so you can say it like in a simple sentence. And it has to be so well defined that you know from that definition exactly what variables you need and the type of study that you have to do and how to gather the data. Without that very specifically defined problem, you can't do those other things. Or if you tried to do them, you could make serious mistakes, right? You could find out later that you picked the wrong variables. Oh, I missed something. Oh my God, I'm gonna have to start all over again, type of thing, right? So that can happen. People run into that. That's why you have a research committee, because they don't want you to do that, right? And waste everybody's time. So all these other steps depend on defining the problem very specifically, deciding the type of data, the variables, deciding how to gather the data, whether you're going to, whether you're going to use what type of sampling procedure you're going to use, how you're going to collect the data. I mean, if you're going to do a questionnaire, for example, now Steve, you didn't do a questionnaire in yours, probably more science. Yeah, yours is involved more measurements. But in this case here, you might, if you were going to do like a political poll, then you might want to decide whether you're going to use the telephone, you're going to use, you're going to mail something out, right? Whatever, the way you were going to collect the data. Once you collect the data, it becomes easier, hopefully, to analyze it, but you're going to have missing data. That's a real problem if you have missing data. Maybe not so much with what you did, Steve, but and more social science type situations. You might have lots of missing data. You analyze it, you draw conclusions, report the findings, and then of course you may decide this may lead to additional research that you do in the future. You need to know all this. I know it's common sense, but it's not something we're going to be doing in this course. But just keep these points in mind when we actually look at some of the procedures that we do in the future. Again, the sources of data, I've gone over it, the difference between primary and secondary. Again, this is, okay, it's okay to know this. It's not critical to know this for this course. Here are the different types if you were going to do a survey. Now, you have to understand an introductory course is going to focus more on surveys and less on what? Experiments. Because every field of study has their own experimental methods. And experimental methods are complicated. They're not easy to understand. So typically, you don't see any description, deep description of experimental methods until you get to graduate school, right? There's no courses on it. I got my master's degree in statistics. That's where I took a whole course on experimental methods. That was it. It wasn't even on any surveys or anything. It was all about experiments, type of designs and all of that. But that's something you see in graduate school. So this course, more like surveys. And again, this is the types of surveys you can do. The thing about surveys is most likely you're going to do a sampling survey. That means you're not going to do a census. You're not going to talk to everyone in the whole population. You're going to take a sample of the population. And because of that, whatever results you get are not going to necessarily match the results that you would get if you did a census, if you talk to everybody. All right, there's going to be what's called sampling error. Sampling error is random, it's not directional. And it's basically, if you were going to measure it, it would be the difference between your result and the true result of the population, which unfortunately is unknown. If it was known, you wouldn't be doing the sampling, right? So sampling error is really the fact that your sample results will be different from your population results. And if somebody repeated what you did, they would get different results than you got. Highly likely that would happen, right? If you wanted to calculate the mean, like this light bulb example we just went through, right? It was a survey of 80, right? What if somebody else did another survey of 80? Would they get exactly the same? No, they wouldn't get the same results. So sampling error has to do with sampling variability, and the fact that these sample results are going to be different than what you would have gotten if you knew the population. Now, non-sampling error is basically biased results, okay? And you're going to end up overstating or understating the true population parameter in a certain direction. And the best example of this would be basically a poor measurement. Let's say you were simply weighing people. Maybe weight was part of the thing, something that you were doing as part of your research, weighing people. Well, if the scale that you're using wasn't perfect, maybe if you have nothing on the scale, it doesn't show 0, it shows maybe 2 pounds, right? So it's slightly off. That's an example of non-sampling error, because everybody's weight's going to be 2 pounds. It's going to look 2 pounds heavier than they really are. So non-sampling error comes from what? Poor measurement, poor instrumentation, the sample design itself is poor. These create biases in the results. Now, it's almost impossible to get rid of all bias. You do your best to minimize it as much as you can. But you should know the difference here between sampling error and non-sampling error. Sampling error is natural variability that occurs through sampling. But the sample results are going to be, even if you had no non-sampling error at all, you're going to have sampling error. Because sampling error is due to the fact that you're just going to have different participants in your study every time you rerun the experiment or rerun the study. Now, here's another important distinction that you should know: the difference between, in general, an experiment and an observation. An experimentation, I would call that a randomized experiment. That's my term for it, randomized experiment versus an observational study. In general, a randomized experiment, you are trying to control the conditions of the study. It's unnatural setting, basically, in an unnatural setting. So basically, let's say you have a new drug that you want to test on a disease, right? It's a pill. And so you have one group that's going to be taking this pill, and then there's another group that will take a pill that looks exactly the same, but does not have those active ingredients. It's basically what they call a placebo. Now, how do you, in a well-designed experiment, how do you assign people to these two groups? You randomize them. You randomly take people and put them in these two groups. You don't purposely put them in those groups. You randomize it. In other words, let's say there's 20 people in your study. You can list them 1 to 20, and then use some sort of random number generator through a computer or something to pick those numbers. All right. So that's what you do. And why do you do that? It's because you want to create two equal groups, equal in the sense that they're sort of equal in other respects, other than what you're testing, right? The treatments that you're giving to the two groups. You want that to be the only distinction between those two groups. So you create this randomization process. You randomly select people for the treatments, the two treatment groups. Now, of course, it gets more complicated than that, but that's in general what happens. And they use this term independent variable and dependent variable. The independent variable is your treatment, right? It would be the pill. The two groups. You have the real pill and you have the fake pill, the placebo. The dependent variable is what you are trying to affect. In this case, the disease, the level of the disease. So you're going to measure the level of the disease. So basically the change in the treatment, right, is going to supposedly have an effect on the dependent variable, in this case, the disease. Now, when you equalize the two groups, then these other factors that could be influencing that disease will get negated, will get washed out, and you're left with simply, did this pill work? And therefore, in a well-designed experiment, a researcher can say one thing caused the other. They can talk about cause and effect. Now, in an observational study, there is no controlling of the conditions of the experiment. Now, for example, let's say you were interested to see if somebody took heroin, would it be a bad thing for the person's liver? I know, I'm just making this up, all right? I don't know if heroin damages the liver or not, but let's assume it does, all right? That's the theory. Could you do an experiment with heroin? The answer is, I don't think so, because you're not going to take a bunch of people participating in the study and say, I'm going to randomly assign heroin to half of you, and the other you're going to get something that doesn't kill you. It's unethical to do that. Now, there are stories of people in the past who've done things unethical like that. But in general, you have to do an observational study. You can't control. So basically, you have to find people who've taken heroin, right? And then you have to watch them over time and see if they acquire liver disease. And maybe you can compare them to another group of people who haven't taken heroin. But the important point is you're not controlling the conditions of the experiment, of the study. And that's an observational study, which sometimes you have to do because you can't do in an experiment. So that's the difference between those two. Now, with an observational study, because you're not randomizing people to different treatment groups or different groups, then it's possible that other variables could be playing a role in the results that you're seeing, other than the one that you're studying. And these are called confounding variables. They don't talk much about that in the book, but just know what confounding variable means. Another variable that is out there that could be influencing the results of your study, and they could be something other than the independent variable or treatment that you're actually looking at, that you're actually determining, if it has any effect on the response variable. So let me give you an example of that. I'll just give you a quick example. We'll be stopping in about 5 minutes. The quick example is, suppose you owned a coffee shop and you wanted to increase the number of people coming into your coffee shop. So you hire, you think, oh, maybe I should just make it look nicer, the place look nicer. So you hire an interior decorator, and this person comes in and recommends changes to the way your coffee shop looks. Suppose at the same time this is happening, a new mall is opening up a couple blocks away. So you redesign your coffee shop and you find more people coming into your coffee shop. But at the same time that your coffee shop is renovated, this new mall is opened up. And the question then is, did the renovations of your coffee shop lead to an increased number of people coming into it, or was it due to the mall opening up? The mall opening up or not, that's the confounding variable. That's the variable that could be determining the fact that you're getting more traffic into your coffee shop. And it may not have been the interior decorating that you did. Okay? So in a observational study, you don't have control over the confounding variables. Now, if you happen to know them, and we'll find out this a little bit later in the course, you can build them into your statistical model to negate the effects of them. But unfortunately, you may not know all the confounding variables that are out there. There might be unknown ones that are causing the changes in your response variable, in your dependent variable. So we'll talk more about that later, but just know that an experiment, well designed, you can talk about cause and effect. Observational study, you may be able to talk about correlation between two variables, but you may not be able to talk about cause and effect because you're not controlling for those confounding variables. That's all I'll say about that. And then I want to spend the next 5 minutes and this is important for this chapter, and then I will be posting something in Canvas that will describe this in more general, but the types of sampling methods. Now, in general, a probability sample means that there is an assigned probability that everyone in the population has to be in that sample, right? If you have a sample, an assigned probability. In most cases, the same probability, all right? Now, a simple random sample means, now they don't do a great job in this book describing this, I have to tell you, it's not really great, but it's okay. A simple random sample means that not only does everyone have an equal chance of being selected, but let's say we wanted to have a sample of size 100, another 100 people in our sample. A simple random sample says that every sample of size 100 would have an equal chance of being the one that you ended up with, all right? There could be 10 million different types of samples of size 100 that you could have come up with, and the one that you got has an equal chance, has the same equal chance of being that sample as opposed to any other possible sample that you could have chosen. So that's really what a simple random sample is. But basically, if you have, let's say you had a population of 1,000 people, and you want a sample of size 100, you can simply list all those 1,000 people from 1 to 1,000, maybe list them numerically, and then again, random number generator will pick 100 numbers out of the first 1,000 numbers, and those people that have those numbers that were selected would be in the sample. It's as simple as that. All right, make sense? That's a simple random sample. Now, a systematic sample works a little bit differently. This would work more like if you had a phone book, the old-fashioned phone book, or even if you had an assembly line. Anything that works in sort of like a progressive way, like a phone book or assembly line, where you're going from one name to the next. A systematic sampling says the following. Let's say I wanted a sample of 100, okay? How do I get the sample of 100? Well, one way of doing it, according to systematic sampling, is pick a number from, let's say, 1 to 10, something like that, from 1 to 10. Randomly select a number from 1 to 10. So suppose you pick the number 8, all right? Then what happens? Well, the number 8, the 8th person in that list would be selected, and then you pick the 10th after that, the 10th after that, until you get all 100 people that you need, all right? Another way of looking at it is boxes off an assembly line. You want to check for defects, all right? Suppose you know that 100 boxes are going to come off the assembly line every day, all right? And you only want to check 5 of them. Which 5 do you select? Well, you randomly select a number, and then you pick so many boxes after that, a fixed number of boxes after that. Where's the randomizing occurring? On that very first box. And then each box after that is so many after that each time. Maybe the 20th after that, like that, continuing until you get all 100 boxes that you want to look at. All right? You get the idea? Systematic. All right. Now, there are a couple of others, stratified and clustered. This is more like if you were dealing with groups of people, groups within groups. Suppose you could take your population and break them up into non-overlapping groups. Good example would be, suppose it's a school district, and ultimately you want to sample school children, all right? So you break your school district into schools, right? Let's say the school district has 5 high schools, 4 large ones and 1 small high school. And you want to ensure that that small high school is going to be in the sample also, all right? So what do? You do a simple random sample of each of those high schools so that every high school is represented in the sample. So you break your population up into non-overlapping groups so that the whole population is broken up. And then you do a simple random sample within each of those groups so that you have your sample size that you need. And then that's it. And it's called a stratified sample, where these groups are called stratum. All right? Now, suppose that that's not what you want to do. And by the way, the reason why you want to do this is because each of these strata are considered to be homogeneous. Homogeneous means pretty much similar to each other in many ways, all right? They're like little mini populations. Suppose these, your population is broken up into groups and they're not homogeneous. Suppose they're different from each other. So maybe it's not a great idea to do stratified sampling. What you could do is what's called cluster sampling. So you create these non-overlapping groups, and then what you do is you do a random sample of the groups. And so if you have, let's say, 10 schools in a school district, you maybe randomly select 3 of them. And then every student in those schools would be in your study. That's called a cluster sample. So a cluster sample is you do a random sample of the groups and then select everyone within each of the selected groups. So you see the difference between stratified and cluster? Stratified, break it up into groups, use all the groups and do simple random samples within each group. A cluster sample, you don't use all the groups, you do a random sample of the groups and use everyone typically within each of those groups. That's called a cluster sample. And fine, and so those are the so-called probability samples. Simple random sample, systematic sample, stratified, and cluster. Those are the well-known ones. And a lot of studies that are more complicated combine them together, right? The national surveys and all. They may have stratified, 2 stratified levels and a cluster level, right? They could be several levels of groupings. So they can get quite complicated. But you just need to know in general what these are. And then the non-probability ones, it's almost like, who cares? Because if you can't use probability, everything that I'm going to be discussing in the rest of this course does not apply at all. You can't do anything else. It becomes simply descriptive studies of the people that are in the study and nothing else, nothing more than that. Now, you could use a non-probability sample for exploratory purposes, to do a little study ahead of time to see what variables that you may need to use and things like that. That's fine. But don't use them as if you can apply them to a larger population. No, you can't do that. So these have limited uses, but they're there. A convenience one is the worst because you can picture somebody in the mall, right, saying you need to sample 100 people and 2 buses show up and 100 people come out of the bus and say, wow, I can now be done in the next half an hour. I can just talk to those 100 people. That's convenience sampling. That's terrible. Probably get very biased results with that. Quota sampling looks like stratified sampling, but it's not because you're not doing simple random samples within the groups. So it's also kind of useless. And then they come up with these others, purposive and judgment sampling. You can read through it. They go into more detail about non-probability samples in other books, but this is it. So anyway, I've written all this up, and I will post it. This is the part here, the sampling methods that you need to know. Basically, the 4 main ones. All right, simple random sample, systematic sampling, stratified sampling, cluster sampling, and then you can pretty much lump all the non-probability ones into convenience sampling because that's really what they are. All right. Any questions about what I just covered? That's chapter 4. That's it. I really want to get into chapter 5, probability, because I know that that is a part that some students struggle with, and I want to spend a little extra time on that. So I want to have that extra session and spend more time on probability, which I will start next time. So final thing I want to say to you guys and to people who are Han and to Rose who are not here is, and let me actually stop sharing this, is that I'm going to be posting within the next few days things that you'll be completing on your own. I will be posting a quiz, which will cover, well, let's say 2 quizzes. All right, one quiz will be on graphing, and another quiz will be on chapters 3 and 4, which is basically on some of these other measures that we've talked about, including some of the sampling stuff too. But the quiz is basically, it's an open book, so easy. I just want to give you some grades, okay? So 2 quizzes, and then, so you'll complete those. I'll give you a deadline, which will give you plenty of time to complete them. And then I do want to give you a test, also done on your own, multiple choice type test. Again, it'll be based on chapters 2, 3, and 4, okay? And that also, I'll be working on it over the weekend. And I'll give you, again, enough time to finish it, all right? So we'll be moving into probability next week, but on your own, you're going to have those to complete, plus that little project I was telling you about before, the spreadsheet one with the group data where you come up with an approximated mean and standard deviation. That will be a project grade also. So we'll do it like that, where I'll give you a deadline for each of those things to be completed. There will be, and now that the project, it won't be timed. It will just be a deadline on that. There'll be deadlines on the quizzes and tests, but once you start the quizzes and tests in Canvas, they will be timed. So the quizzes might be 20 minutes each, okay? But they'll be short quizzes, easily done within, you'll get, if you know what your stuff, you can get it done in 5, 10 minutes. The test will be a little bit longer, maybe 20 or 22, up to 22 multiple choice questions. I might give you like an hour and 15 minutes to complete that. Okay. So that'll be done in Canvas. I'll have it set up in Canvas. Again, you just go into Canvas. I'll show you how it works. You just go into Canvas and you'll see it under module and you just click it and get started. So it'll work very easily like that. The project will be something you'll just send to me. But again, I'll have it, more details next Tuesday. Once I have it all set up, I will give you the deadlines and all of that. And you can give it to me, all right? Hand it over to me. But in the meantime, you'll be working on that project. I think that's the one thing that you can work on. And that, I guess it was problem number 3.40 on page 86. I'll be posting 3.41. So again, you're going to duplicate what you saw me do in class today, creating a project in Minitab. Just do it in Minitab. It'll be easier and then just duplicate what I did, except with a new problem. All right, it'll be different data set. It'll be different classes, different frequencies, but the same procedure, the same idea. All right, and I think you'll be easily get it done. All right, any questions? All right, that's it. That'll be it for tonight. So I'm going to turn off the recording.